Cauchy-Euler is next. A Cauchy-Euler equation is a differential equation of this form. Notice that your coefficients are no longer constant, but they do have a particular form. To the nth order derivative of y is attached a power function, an nth degree power function. Named after two of the most prolific mathematicians of all time, Cauchy and Euler. And the quickest way to get shanked is to walk up to a mathematician and say Euler. Any math person with a solve will probably try to kill you for that. It's Euler. If there was a god of mathematics, it'd be Euler. It's actually a joke. You could discover a brand new branch of mathematics, and Euler already has a theorem in it. Method of solution, again, read through it. We're boiling down to auxiliary equations. Now, unlike with the constant coefficients, it's not as straightforward for higher degree, right? So here it's just derived for the second degree. That's your auxiliary equation for second degree. I don't think I've derived it for anything larger than that. That might actually be fun. And this looks derived for a third degree. But notice what is used to derive it. X to the n. Whereas for the constant coefficient, we use e to the n. Or I think it was what, e to the mx, right? That's what was used. Right? As before, that is still a quadratic in this case. Either way, it's going to be a polynomial, right? Which means three possibilities for your roots. Distinct real roots. So that's distinct real roots, m1, m2, two solutions. X to the m1, x to the m2 are your linearly independent solutions, right? So in general, no matter what the degree is, if it's a distinct real root, it's x to the m as one of the linearly independent solutions out of it. If it's repeated, right, then we use the reduction of order. Go through all that, and you'll wind up with x to the m1 times natural log of x. as your second independent solution. Each time that root repeats, you multiply by another natural log of x. Right, so what was it for the constant coefficient? It was each time it repeats, you multiply by another x. Here, it's you're multiplying by another natural log of x. And finally, if you get complex conjugate roots, remember, if you get a complex root, its conjugate's also a root, so they always occur in pairs. You'll get x to the alpha plus beta I and x to the alpha minus beta I as your linearly independent solutions. But we don't like that. Those are complex value solutions. We want real value solutions. So in terms of real value, x to the alpha cosine of beta log x and x to the alpha sine of beta log x are your two linearly independent solutions from the complex conjugate pair of roots. And that is for the homogeneous part, which remember is your complementary function. If it's not homogeneous, then you have to find a particular solution, and you have to use variation of parameters. You cannot use undetermined coefficients, the Cauchy-Euler. Actually, that's not true. You can. What I'm going to do is look at third order Cauchy-Euler. Try to find the auxiliary equation. So again, we're going to try y equals x to the n is our solution. What's y prime?
Mx to the n minus 1.
What is y double prime?
N times n minus 1 x to the n minus 2.
And now we need third derivative. Which is what?
The second derivative times n minus 2 x to the n minus 3. N times n minus 1 times n minus 2 x to the n minus 3.
Now plug them in. Notice what one's attaching. Every term has x to the n. There's the auxiliary equation. But let's get it into the more standard polynomial form. So expand out that n times n minus 1 times m minus 2. M cubed, right? Minus 3m squared plus 2m n times n minus 1, n squared minus n. Right, that's just plus cn plus d. An cubed plus b minus 3an squared plus two a plus c minus bn plus d equals 0. And there's your auxiliary equation for third order Cauchy-Euler. And to be a similar process, if it's a fourth order, fifth order, so on and so forth. It's like I said, unlike the constant coefficients, the auxiliary equation doesn't naturally flow. Let's look at the auxiliary equation. Was what? A times m squared. What is A?
X squared.
1. That's supposed to be plus b minus a times n. What is b?
3. X.
Negative 3.
Oh, negative.
And we said a was 1, so
Yeah.
negative 3 minus 1.
Negative 4.
And that should just be plus c, right? Plus c equals 0. What was c? Negative 4. There's the auxiliary equation. How are we going to solve that? That is one correct answer. Let's pretend we're not allowed to use calculators.
Quadratic.
Yeah, this can't be factored with integer coefficients, so we have to use quadratic formula. What's the quadratic formula?
Opposite b plus or minus a squared minus 4ac all over 2a.
So it's opposite of b, plus or minus, what did you say?
Square root of a squared, so 16 minus 4ac
That should be plus 16, right?
all over 2a. 2.
Oh, look at that. 4 plus or minus the square root of 2 times 16, which is just 4 root 2, right? Two plus or minus 2 root 2. Those are distinct real roots, right? So come up. Distinct real roots. X to the m1 and x to the m2 are your two independent solutions. And there's your general solution. So very similar to what we've been doing. What is A? What is B?
Four.
And A is 1, so 4 minus 1. And what is C?
15.
There's your auxiliary equation. Can that be factored using integer coefficients? Factors of 13 when added give you 3. There are none. So no, it cannot be. So we have to use quadratic again. So we get what? -3 plus or minus the square root of 3 squared minus 4ac. 4 times 13 is what?
52.
52. Right away, you should be able to tell what your roots are going to be. What should the 3 cases will be? What's 9 minus 52? Easy way to do it. What's 52 minus 10? It'll be -43. And 52 minus 10 is 42, then just add 1 to it. We get complex conjugates. Again, 2 ways to write it. Because there's going to be an x to the alpha common in both of them. So you could just factor that x to the alpha out, which I think I will do. Right, remember, alpha is your real component, and beta is your imaginary component. X to the alpha times C1, then there's what? Cosine of beta log of x. But there's another way of writing that, isn't there? If we come back up here real quick. Can we write it as natural log of x to the beta? You can do either way, I don't care. I think it's ultimately going to depend on what we're going to wind up doing with it. I personally don't like the way that looks. I think that looks better. Keeps it symmetric. And that would be the general solution.
possibility.
For this problem or in general?
In general.
For second degree?
Yeah. Got it.
Give me the auxiliary.
M squared plus 3m plus 1.
Plus 2m.
Oh, I'm sorry, I was simplifying that. Gave me
And
Plus 1.
all right, remember for Cauchy-Euler, it's B minus A all times.
yeah.
For second degree. Can that be factored? Where's the factor to?
M plus 1 squared.
And it's repeated, right? When it repeats, what do we multiply by?
11.
Or, we could write this, right? Oops. I hope this was meant to be an initial value problem. Oh, there's the general solution. We're supposed to have those. So now we can find C1 and C2, right? Let's copy what we said this is. I have to choose between do a product rule or a quotient rule. Product. Either one's. Bad noise. I think I'm going to do the quotient. What's the derivative of C1 plus C2 log of x? Not 1 over x.
C1 plus C2 over X.
You have too many terms.
C2.
It's just C2 over x. C1's a constant, right? So that derivative is 0.
Oh.
And then log over x, or log of x, its derivative is 1 over x times that constant multiple. Minus times derivative of, oh, this one's a tough one. What's the derivative of x?
1.
Oof, how'd you get that? That was very difficult. X squared. Which is just what? Negative C1 plus C2 times the quantity of 1 minus log of x for the numerator. If we now use the initial conditions, what's log of 1?
0.
Oh, that's sexy. That immediately gives us C1. We already know what C1 is. And log of 1 was 0. Right, negative 1 plus C2 all over 1 squared. And that has to equal 0. Which gives C2 is also 1. Question? They say it should be 1 minus log x over x, and that's definitely not right. C2 is not negative. Oh, wait a minute. Okay, C1's wrong. That's our solution. 1 plus log x over x. Now one that's non-homogeneous. All right, so remember the first thing we want to do is to find the complementary function. How is that done? It's just the solution of the homogeneous component, right? What's the auxiliary?
It's going to be m squared plus, not minus 1m, because you're taking b minus
A minus A.
which is 2 minus 1, so you're at m.
Plus M, right? Not
Yeah,
minus
plus,
M.
plus m.
You're right the first time. Don't question yourself.
Plus, or minus 8.
Is that an equation?
Equals 0.
Now you have an equation.
Okay.
There's your auxiliary. What are the solutions to that? It's obvious. Obvious. There's your complementary function. Now we actually can use undetermined coefficients. And I think for this one it's going to be easier to do that. Because what does it equal? What's the g of x?
6x to the 0.
That's a third degree polynomial. But do I trust this? I'm questioning. I've never used undetermined coefficients for Cauchy-Euler. So let me just double check something. No, it does work out okay. So it's going to work a little bit differently for Cauchy-Euler than it does for what we were doing before. Before, we would have to do a general third degree polynomial. Here, we don't have to. Cauchy-Euler, we can just do the power function, ax cubed. We need first and second derivatives. What's the first derivative?
X squared.
What is the second derivative?
Six AX.
Now plug everything back in. Was x squared y double prime plus 2xy prime plus no, minus 8y. Why did I do 6x cubed? I was looking at g, not yp. It's what, 6ax cubed plus 6ax cubed minus 8ax cubed? which is what?
Right.
And what does that have to equal?
6x.
Has to equal g of x, right? 6x cubed. What's a?
3 halves.
What is it?
3 halves.
3 halves. Right, or 6/4 simplified. The particular solution is 3x cubed over 2. And the general solution was what? How would you find the general solution? Through the power of technology. I don't have to rewrite that. There's your general solution. Right, it worked nicely here because that x cubed wasn't in the complementary. Right? The power 3 wasn't in your complementary. If it was, we would have to multiply by a log x, I believe. Right? Or you could just use variational parameters, you don't need to worry about that.
When you use variation of parameters, do you, like in this situation, there was a x cubed in front of the y to the 3rd degree, would you divide everything by that a, and then in variation parameters use g of x as a simplified version?
For variation of parameters, I believe you'd stick with the coefficients, not necessarily the x squared. So you'd leave that x squared alone.
Like g of x would stay 6x cubed rather than 6x.
Yes. Let me double check that, but I'm pretty certain. Would. I think you have to worry about dividing by that x squared. I could be wrong. Oh. Okay, that you both not even do non-homogeneous. That's nice. Textbooks. Where's it here? Oh, tell me this book doesn't have Cauchy-Euler. Of course it won't. Oh, it does. That wasn't it. you would have to divide by the x squared.
Okay.
Yeah, so in this case, your g of x would be 6x. But then everything else is the same. Right? Your y1 is still that hideous looking power. Y2 is that hideous looking power. But that's what calculator is for. Wow, I used the shittiest of the textbooks to write up those notes because those are very good notes. And it did variation parameters, and these two didn't. So it's pretty sure this textbook's like $300 now. I get it for free. Advantages of being the instructor. They send me free books. Disadvantage, they send them to me and then they want me to review them and recommend that we use them. Because then they make money. Questions? So this was our first look at non-constant coefficients. I started with Cauchy-Euler for reason, because it is the easiest case of non-constant coefficients, of variable coefficients. If you pay attention, I skipped 2 sections. This was 7.4. 7.1 I just skip altogether because it's just a review of power series. That's Calc 2. I skipped 7.2 and 7.3. Because in general, if you have variable coefficients, you have to do a power series solution. And those are pain in the ass. There are 2 possibilities. What's known as an ordinary point. It's just that your coefficients are defined. Right, so once we have 1 over x, 0 would not be an ordinary point. And then you have what's known as singular points, which are non-ordinary. And the method is different depending on the point. Right? Because remember, if you remember from Calc 2, you can expand any function as a power series centered at some point A. Generally speaking, we're trying to center it at 0. But if 0 is a singular point, you'd have to use what's called the method of Frobenius, which is even worse. I'm actually skipping the method of Frobenius. And we'll just say, we're just always going to consider an ordinary point. If 0 is not an ordinary point, we'll pick another point to expand along. But it's still extremely tedious. And you'll see. I finished 20 minutes ahead of schedule. Perfect. I'm going to give you an extra credit opportunity. Because a lot of you are not confident on that first exam. Even though I'm currently grading, and they don't seem too bad so far. I did throw a question out, though. Throw out question 7. So it's at 54 instead of 60. Here's your extra credit opportunity. Get into your groups.
Yeah.
Derive the auxiliary equation for the 4th order Cauchy-Euler. don't know if Jack reached out to you.
No,
Did Jack reach out to you?
yeah, he was pretty
He's
young,
he's
so
very sick.
So we start with
He got
one
sick
with
yesterday.
XTM.
we were talking, I was gonna talk to him about that, like the report project and stuff.
We would start with one with
He mentioned
XTM,
me
and then
yesterday
report to
that
the
he was
report.
gonna be on hospital.
Yeah. I think
Like,
we-
He's in my Cal 3 as well. He got sick. in my
Yeah.
Cal 3.
It's the third.
And then Drew reached out saying he dropped the course and,
Even though he's still on the roster.
yeah. So now I'm stuck.
You're supposed to go to 210, so at 210 I'll hand out the worksheet. It's about 15 minutes from now.
Just to make sure. No, yeah, we will start with AI, so it's one report, yeah. Thanks.
Turn to the worksheet.
Okay. So each person? Yeah.
Just gonna hand out the worksheets now. You can turn in the extra credit with the worksheet, just keep the work separate. Right, so that should be its own separate sheet. Make sure all of your names are on it.
Did you all put in? Yeah.
Function is analytic if it can be represented by a power series centered at the point. So we say that your function f of x is analytic at A if there's the power series expansion for f centered at A. X equals x naught, ordinary point of the differential equation. I'm doing second order, but this extends to any order. If, when you write your equation in standard form, then all of your coefficients are defined at the point. They're analytic at that point. Point that's not ordinary said to be singular. As I mentioned, we're going to focus only on ordinary points. We will not look at singular points. through that, blah, blah, blah. Theorem. It's fine. Finding series solutions is generally a pain. Well, if you look here, 0 is an ordinary point, right? We're going to center our power series at 0. We're going to say this is the form of our solution. What we now have to do is find base of n. Now, here's the good news. This problem's only asking for the first 3 non-zero terms instead of the entire power series expansion. What is y prime?
Would the sum stay as is? And then we just take,
That's part of the question, isn't it?
yeah.
You have to remember Calc 2. Remember, when you take derivatives, you lose a term, specifically a constant. We now plug these back into the differential equation. Y double prime minus x times y. Remember, we can shift the index. want to write this. It's a single sum. So that's where we're at right now. Should I have done that? I think what I want to do is strip that x3 first. That's what I wanted to do. So I want those x's that have the same exponent in the indices to start at the same value, ultimately. Take up first two terms of this. Then I can move up that equals 2, right? So that's what those first two terms are, negative a naught x minus a1 x squared. Still need to have those be the same power. And then I have to take 2 out of 2 of 9. Equals 3 right there. Oh, that's hideous. I have to take 3 terms out of that first summation too. To finally be able to shift everything. Tap x to the n. Oh, that's hideous. I don't like that. I get kind of serious solutions. Let's try that, see what that gives us. So first 3 terms out of here. 2 minus 1, 2, so it's what, 2a2? It's what, 3, 6, 8, 3. And 4, 12a 3x squared. Or sorry, a4. Then minus those. So I'm not right every time. I want to make that. So I want to shift that down by 2, right? Because I'm adding 2 to everything, which makes this n plus 2 times n, a to the n plus 2. We'll make that x to the n. This is just hideous. Now combine these. That whole thing has to equal 0. This should now be a coefficient comparison problem. Yes, it is. A2 has to be 0. That's nice. He gives A2 has to be 0. X's, we get 6A3 minus A0 is 0. A0 has to be 6 times A3. And we have to have this. That is the recurrence relation. If you solve for it, this is the important one there. Oh, that's good. We're going to be able to get everything really in terms of A1 and A0. Which is good. Yes. Good. This is what I want. I want my track. Now I just have to go through all these. Now remember they said they want the first 3 non-zero terms, right? So that is what we're going to put next time. This is why I hate power series solutions. Again, do you think this is bad? Singular ones are even worse. Which is why I'm just skipping them a little bit. I'm happy I got there. We can see Tuesday. Oh, I'll put this up too, I guess.